Hello my YouTube friends. Today we're going to look at circuit analysis, especially looking at mesh current method and the node voltage method. So these two methods assist us in solving resistive circuits, as we shall see. So first of all, we begin by understanding what a loop is and the difference between a loop and a mesh. You notice here that we've got loop 1 and loop 2 here, and then loop 1 is composed of these three elements that is in a closed loop, so there's no open circuit in this loop. And then loop 2 is composed of this loop. And then if we take the outer connection of the elements, excluding this element, that is that element, we have what we call the outer loop. Now this is where the difference comes in when we look at a mesh. A mesh does not have another loop within it. It's just one loop. Another component that you need to understand, or another aspect that you need to understand, is the definition of a node. So a node is a branch, is a junction where two branches meet, and that is what we consider as a node. Now, when we look at what a mesh is, you find that, like I explained, there's no other mesh within it. It's just one mesh. So when we come here, we have mesh 1, mesh 2, mesh 3, and mesh 4. And that is the definition. So it's a loop that does not contain other loops within it. That composes, or that formulates what a mesh is. And we use this mesh to form what we call a mesh current, which is defined, in my case, I like to define it clockwise. So this direction is clockwise chosen, and using that, we are able to create a mesh current and solve the mesh currents by applying Kirchhoff's voltage law in a closed loop or in a closed mesh. The number of equations that you are going to make are going to be equal to the equations, the number of meshes that you have in a particular circuit. For instance, in this circuit, we have 4 meshes, and therefore the number of equations that you are going to make are going to be equivalent to the number of meshes. Now, there are 3 scenarios that you are going to face. One is when you have a voltage source in a mesh circuit, and 2 is when you have a current source which is situated not in between the 2 meshes, and 3 is when you have a current source situated in between 3 meshes. For this scenario that we have here, the first case, which I haven't put as a case, I've taken the cases to be only where we have the current sources. But in this case, we simply apply KVL where we have a voltage source. We know that KVL should be equal to the sum of voltage sources should be equal to the sum of voltage drops. So this forms KVL. So in this case, we've got the voltage source, which is just one source, and then we've got a voltage here if we had to add. So where the current enters a resistor becomes a positive minus, so VR1, and here we have plus minus VR2. So according to mesh 1, these are the voltage drops that we have on resistor 1 and resistor 2. Therefore, to formulate KVL, we simply have the voltage source must be equal to the voltage drops, VR1 plus VR2. And this is what we are formulating up here. But what is VR1? VR1 is simply the mesh current multiplied by the resistor. So VR1 is simply equal to the mesh current, I1 in this case, multiplied by resistor 1. But when we come to the voltage drop across resistor 2, because there's a shared current which is coming from mesh 2, therefore this resistor has shared current. So you've got I1 and I2, but because our main mesh is I1, we're going to subtract the current from mesh 2, which gives us R2 I1 minus I2, and this is what you see here. So the voltage drop across resistor 2 is given by that. And then if you come to now analyzing the cases that you are going to have, in a mesh where you have a current source, that implies that there's no need for you to make a mesh equation depending on the direction of flow of your mesh current. Then that current source is going to be the value of the mesh current. For instance, in this case, we've got the current source which is pointing upwards, and then you've got a mesh current I2 which is pointing downwards. So in this case, I2 is the opposite in direction to IS. Therefore, I2 will give us a minus IS. And that is how we solve these circuits. So when we come to checking the second method, the second scenario. The second scenario is where we have what we call a super mesh scenario, and that is what I'm calling the second case. This is when a current source is located in between two meshes. So you're going to make two equations. One equation is what we call equation at the super mesh, which is considering that super mesh, and then equation on the current source. And this equation at the current source is obtained as I will show you. So when we look at this circuit, we have the voltage source, resistor 1, resistor 2, and resistor 3. These are resistances that are going to be considered in what we call a super mesh. And to formulate an equation, we apply Kirchhoff's voltage law accordingly to this outer loop, which is called the super mesh. So we begin by explaining KVL, that the voltage source must be equal to the voltage drop. So we have the plus minus, there's a voltage drop there, and there's another voltage drop on resistor 3. And therefore our equation in this case is the sum of the voltage sources, in this case which is just 1. You should also bear in mind that if the current flows out of the positive terminal, then that voltage source is going to be considered a positive voltage source. If the polarities are reversed and the current flows out of the negative terminal, then you expect the voltage source to be a negative source. So in a place where you're going to have several voltage sources, you have to be very careful in the way you sum them up, looking at the conventional polarities. So in this case, we have VR1 plus VR2 plus VR3. This is what forms our KVL equation at the super mesh. And therefore, when we come to compiling what VR1 is, we look at which current is passing through that resistor. In this case, VR1 is equal to R1 multiplied by I1. And when we come to R2, we have R2 multiplied by I2. This is the current that passes through that resistor. And when we come to R3, we've got I2 passing through. So this should be I2 passing through resistor 3. And that forms the equation at the super mesh. But when we come to forming the equation at the current source, we have to look at how the two currents are being affected by each other. So when you look at, in this case, what you have is the resistor, the current I1 is in the opposite direction to the current IS. You can either formulate KCL at this node, or you can formulate KCL at node A. So node A and node B can be your guidance. For instance, in this case, when we look at node A, you have the sum of currents entering that node. In this case, if you look at the current I2 in this direction, IS entering, and then I1 entering also. So you've got I1 plus IS equal to I2, which in this case, we are considering it as leaving this node from there. And from there, you can formulate to say IS is equal to I2 minus I1. And that's your equation formulation. IS is equal to I2 minus I1. And that is the way we form the equation, what we call the equation at the source. Now, let's look at a few examples. Let's look at a few examples. These are the two examples that will be looked at. One is an example where we've got the current source in between two meshes, and then the other is where we have a current source on the edge of a mesh, and then we have a voltage source, and basically we've got three meshes. So in the first example, you're being asked to find the currents through resistor 1, resistor 2, and resistor 3. Okay, and using the mesh currents, we're able to determine those currents. Therefore, watch the next video so that you can know how to solve these equations and circuits and analyze them properly. Thank you and good day.